Okay, so for 12.3, we're going to investigate a new type of pattern. It's a pattern that you would have seen before. Let's say I would have given you numbers like 3, 6, 9, 12. You might wonder what's coming next. 15. And you could say, well, that would be something arithmetic, right? This is review. This is review where you could say each time we're adding a 3, right? But what if instead I would have given you 3, 9, 27? What do you think the next one would be? 81. This is the new stuff that we have today. This is not an arithmetic pattern. We're not adding a fixed number, or we're not dealing with a common difference. Instead, how did you find the next term here? You'd multiply by a 3. Now, sometimes kids would say, oh, it's really an exponent kind of a property. Well, you could kind of look at it that way, but what if I would have given you something like 5, 15, and then 45? You get the idea. You'd say I'm multiplying by 3 each time. And there you couldn't get away with saying, oh, you're raising up to a power, right? I guess you could look at that previous one, this one right here, in addition to just multiplying by 3, you could have looked at it as powers. Whereas this right here very clearly is geometric. Geometric, what are we talking about? When the ratio of successive terms is always the same. When 45 divided by 15 happened to be 3, 15 divided by 5 was equal to 3. We're not looking at a common difference. We're looking really at a ratio of successive terms. And that's really what we're seeing right here in this box. You'd have a beginning. You'd have a sub 1 is some starting value. But if you'd always divide successive terms, getting the same constant, getting that same ratio, calling it R, this would be a geometric kind of a pattern. Now, of course, ironically, we're dividing, and yet very often when kids will say, you're multiplying to get to your next term, you can think of it that way. But as you multiply, that means that you'll have a fixed ratio. So right here, we've got a recursive definition. You'd always have to start with something, with a sub 1 being given to you. And then if this is true that a sub n over a sub n minus 1 is always fixed, we could multiply both sides by a sub n minus 1. And as we do that, these cancel out. And this is where you would get what we see right here. Okay? So the question for number 1, it's just pretty much a yes, no. Is this sequence geometric? What do you think? Yes, it certainly appears to be. Why? Because 6 divided by 2 is 3. 18 divided by 6 is 3. 54 divided by 18, we could confirm, is 3. 162 divided by 54 is 3. Yes, we have a common ratio. We definitely have that to be the case. So that's just a yes-no kind of a question. As we look at number 2, it will say, show that the following sequence is geometric. And then you could think, well, my gosh, how do we do that? And then later on, they want you to find a first term and find a common ratio. Well, guys, look, if t sub n is equal to 3 times 4 to the n plus just n, that's given to us. You might wonder what the following term is, t sub n plus 1. Wouldn't that be 3 times 4 to the n plus 1? Would we agree with that? Usually kids would say, sure. Well, let's take that ratio. T sub n plus 1 divided by t sub n, we'd have this right here. And, you pretty much can see a couple of things happening. The 3's cancel out. And what's 4 to the n plus 1 divided by 4 to the n? Just a 4, right? You've got one more factor of 4 up above. So this is a common fixed ratio, so we can say, therefore, this is geometric. We're writing this abstractly. But then they're saying, would you find the first term? Would you find the common ratio? By the way, what is the common ratio? We just found that. 4. Now, look, you could go ahead and generate this. You could say, I wonder what my first term is. First term, plug in n equals 1. What would this work out to? 3 times 4 to the 1. What is that? 12. And we could say our second term, if we wanted to find it, that's 3 times 4 to the second. 4 to the second is 16. 16 times 3 is 48. You could keep going with that, and then you could clearly even see the common ratio, taking place. But what's your first term? Your first term is 12. That's the other thing that they're asking for us to show. All right? So you might wonder what this pattern is really all about. If you're always multiplying 4, if you're always multiplying by 4, take a look. You'd have a sub 1. Your next term would be a sub 1 times r. You're multiplying by r, right? And then you'd go to your next term. This is my second term right here. You'd say, what if I go to my third term? Well, I'm going to multiply by r again. So I'd have a sub 1 and then multiply by one more r. Wouldn't that become r squared? Right? And then you'd say, well, what if I went to my fourth term? You'd say, well, I'm going to multiply by r again. That's your fixed common ratio. Well, now I've got a sub 1 r to the third. What are we seeing? We're seeing that, if you've got your fourth term, how many times did you multiply by that common ratio? 3. You didn't do it for the first term, right? There's that offsetting. For the third term, you could see that I only multiplied by my common ratio twice, and so forth. So you can begin to wonder, well, what if this kept going forever and ever and ever? You might say, what if I had an nth term? What do you think we'd have? R raised up to the n minus 1. Do you see what we're talking about? For the fourth term, it wasn't r to the fourth. It was 1 less for the exponent of r, wasn't it? And that's where this formula is really coming from explicitly. They're saying, look, if you want to find the nth term of a geometric sequence, it's the first term times the common ratio raised to the n minus 1 power. So, wow, as we're looking here at number 3, wow, guess what your first term is going to be for number 3 in this pattern? A 10, right? That's very clearly your first term right there. What about your common ratio? What about r? What do you think r is? 9 over 10. Look, this is especially helpful when you could say, could I just divide successive terms? Right? That's a way to help you see. I've got 9 tenths. So let's answer these questions now. For part A, they're saying find the nth term. Well, the nth term is going to follow from this formula right here. We're going to say take your first term. Your first term was 10. And my r is 9 tenths. And I'll raise it up to the n minus 1 power. And there we have it. We've got our formula for an nth term. Well, you could algebraically get the 10 and the 10 to the n minus 1 to reduce, but you don't even have to deal with that. You could just write it this way. That's a good question. Let's find the 9th term. Let's let n equal 9. And you could think, well, my goodness, how do we do that? Well, a sub 9 would be 10 times 9 tenths to, well, this is 9 minus 1. So here's where it gets ugly. There will be some times, guys, where, unfortunately, going up 9 to the 8th and 10 to the 8th, that's going to get to be brutally ugly in a hurry. But I'll tell you what, the author really is just asking us to see if we can go ahead and use our calculator to get some help here. Look, you could just type this in pretty much as you see it. 10 times 9/10 all the way up to the 8th power. As you do that, you get about 4.305 roughly. About 4.305. And as you check the answers in the back, you're going to see our author will have to use decimals sometimes, because as you continue going on, you might guess that your fractions would get brutally ugly, and rather than have to deal with these super messy fractions, writing out 10 to the 8th and 9 to the 8th, it's okay to just say, look, we're pretty close to 4.305. Okay? Then what? For part C. Part C, they're saying, would you write this out recursively? Now, recursively means you've got to name a sub 1. A sub 1, we said, was 10. But also, we knew that a sub n was always going to equal r times a sub n minus 1. Our r was 9/10. And a very nice and simplistic looking form here. The recursive form, you can see it looks pretty, simple. The downside to the recursive setup is that to find, say, the 9th term, I'd have to know the 8th term. I'd have to know the one right before it. So that can get kind of tedious. We doing okay? All right. On the back, guys, we're going to deal with a sum. And, just like with the arithmetic pattern, you can have this expression if you add up the first n terms. I don't have time, especially now on the video, but we could prove this. We could show this to be true. At some point, I'd like to, because sometimes this can seem to be so strange where this is coming from. You're saying if you have a geometric series, if you've got a geometric pattern, and if you're going to add up the first n terms, surprisingly, it's going to be this. It's going to be a sub 1 times 1 minus r to the nth divided by 1 minus r. And like I said, we'll deal with that a little later. But take a look at this right here. They're saying, let's just say you've got this geometric pattern. We've got 1/2 to the n, and they're even spelling it out for you. They're giving it to you right here. They're saying, what would that look like? 1/2 plus 1/4 plus 1/8. And they're saying, keep going and going and going and go up to an nth term. You can think, well, my goodness, wow, that's really something. You guys help me out. What's the first term in this pattern? What do we have? 1/2. What do you think our r is? What am I multiplying each time to go to the next one? Also 1/2, isn't it? You see that? It's going to be just 1/2. What are we getting at? You could have a first term and an r that are actually the same number. That can happen. But look, they're saying, no, please tell me what this pattern really is going to work out to, and can we, in fact, maybe clean it up? Well, we could definitely hope that we could. Look, your a sub 1 here is going to be 1/2. And then we'd have 1 minus 1/2 to the n divided by 1 minus 1/2. Now, in terms of cleaning this up, look at that denominator. What is 1 minus 1/2? Oh, and forgive me, this is 1 minus r as I was writing that. It's you could see our denominator, 1 minus 1/2, why I circled,